last time we learned how to draw the reciprocal function, 1 over f of x, and we learned that we need to draw asymptotes where f of x was equal to 0, right? We learned that we needed to draw common points where y equals plus or minus 1, and then we learned to draw asymptotic behavior. Which meant that the lines were usually going to infinity or negative infinity, right? Okay, so you remember that from last time. That was 1 over f of x. The first thing we're going to learn to do today is to draw y equals cosecant x. And what we're going to do is we're going to think that that's the same as y equals 1 over sine x. So it's basically drawing the sine curve, right? And then we're going to do the reciprocal transformation of the sine curve, okay? So there's a lot of stuff here for communication. I'll show you how this works. So let's say we drew this first, our xy. We know the sine curve goes like this. I'm going to do it dashed so you know that it's really not part of the curve. To be very clear, what you should do is you should say that this is y equals sine x. Okay, and we're just going to use it to produce cosecant. It's not part of the actual cosecant graph, right? No, it's not the opposite that way. It's the opposite as 1 over. Okay? If it was just this, that would be just negative sine x. Okay. So it depends on how you say opposite, right? So again, we're going to draw asymptotes. So we're going to do y equals cosecant x in blue. The first thing we're going to do is draw asymptotes where the original function is 0. Oh, we should put some scales on here. Every graph should have a scale. So that's 1. That's negative 1. And this is 2 pi, right? Good. So remember, we draw asymptotes at the x-intercepts. Very important for all these. So we do that. Good. That's step 1. Step 2. Common points at 1 or negative 1, which you can see happen right at the top of the curve and at the bottom of the curve. And then the last thing is to draw the asymptotic behavior, which if you're above the x-axis, shoots to positive infinity, right? So this goes like this. And if you're below, it's below. So that's what the cosecant curve looks like, the thing in blue. Yeah. So secant will be the same, right? Because it'll have, you just draw cosine. It'll be the same procedure, right? But you're going to draw cosine first and do the same with cosine. Is that good? And for the test, you'll be asked to draw one or the other. Half of you will get the test that says draw cosecant. Half of you will get the test that says draw secant. Secant x. Okay? Is that okay? Please write this. The next thing that you're going to be asked to draw is either y equals tan x or y equals cotan x. Okay? And here's the thing. We didn't graph this at all, right? No. If you think about tan being this, tan is sine over cos, right? We did that in our exact value chart, right? To find tan, we always did sine divided by cos gave us tan values. Okay? Also from your exact value chart, if you remember from your chart, the tan of 0 is 0. Which makes sense because if sine is 0, then tan will be 0, right? And if you think about the sine curve, sine is 0 here, here, and here, right? So tan will also be 0 at those same places, right? Are you okay with that? So when we draw the tan curve, Exactly. That's the other part. You're dividing by cosine, right? So where cosine is 0, tan won't work. And when it doesn't work, we draw an asymptote. Okay, and that happens at the half pi's. Now, you can remember both those details, but really, if you just remember one of them, in that tan has zeros at the whole pi's, right? And then you just remember that the asymptotes are halfway in between. That makes sense? So if we put a pi here, a 2 pi here, and we know these are the zeros, that means the asymptotes for tan are halfway in between. Does that make sense? I don't even have to label them, because I'll assume that this is half, as long as I see the scale here, right? Now, the only thing we need to know now is what about the curve? Like, how does this asymptotic behavior occur, right? We know that stuff is going to be shooting up and shooting down. The question is in which direction? Well, if I go on this side, that would be a negative pi over 2. That's a good place to do it. I do know the tan of pi over 4, right? So I'm going to know this. I know the zeros, and this is the other piece of information that I need to know. The tan of pi over 4 is 1. Right? That's from our chart that we all have memorized and we've all been evaluated on? No. Okay. So the tan of pi over 4 is 1. There is that point. Right? Because this is pi over 2. So pi over 4 would be halfway in between there. Do you see that point? Does that make sense to you? That there would be a point there? Once you know that there's a point there, as I go towards this asymptote, what appears to be happening? It's going up because I'm going like this, right? I'm going from 0. So what's going to be happening on this side? It's going to be going down. If you think about this, you can think about it this way too. This angle between 0 and pi over 2 is in quadrant 1, right? So tan is positive in quadrant 1, so these values have to be positive. And if I look about 0 to negative pi over 2, that's in quadrant 4, so tan would have to be negative there. Does that make sense? Okay, so you can think of it that way as well. Yes, quadrant 3 is we haven't done that one yet. Quadrant 3 would be from pi to pi over 2. Or pi to 3 pi over 2. No. You're thinking it wrong. It's not this now anymore. It's because these things represent angles, and the angles are here. Yeah, I can see where that's confusing. Yeah. You think about these things represent angles. This is between 0 and pi over 2. That's actually quadrant 1, from this angle to this angle. 0 to pi over 2. Yeah, I can see why it's confusing because of that. So, if it made sense for you, fine. If not, here's what you got to do, okay? You remember that the tan of pi over 4 is 1. And you know that it's not going to be a parabola, it's going like this. Both tan and cotan have that kind of shape. Cotan just goes in the other direction. I would call this going up, reading it from left to right. I would call it an increasing function. And tan, I would say, yeah. So, cotan, sorry. Now, if I ask you to graph cotan, you know what? We always ask you to draw one period. So if you would actually have drawn one period here, yeah, if I wanted to do the other one, it would look like this. By the way, don't do goofy things with the lines like some people kind of, I don't know what they're doing, but it's just kind of like a half a parabola this way, half a parabola that way. Right? That's the way. That's always what a tan graph looks like. And I would not ask you to transform it. I would just ask you for the tan graph. So if you have it memorized, there you go. 3 out of 3. Cotan is the opposite because it's cos over sine, right? So it's going to have the zeros where cos is. Right, so that's the other way of looking at it. Since sine is at the bottom, cotan will have the problems where sine is 0. And you know what? You don't even have to remember what cotan stuff is. You just can say, well, it's the opposite of tan, right? So as long as I got tan straight, that tan has zeros at the whole pi's, right? That means cotan's going to have asymptotes at the whole pi's, right? Because they're flipped around. Does that make sense? Sine has zeros at the whole pies. Tan has 0 at the whole pies. Cotan has asymptotes at the whole pies. So this is what cotan would look like. Right? Everybody okay with that? And that means it's going to have zeros halfway in between. They share a point at pi over 4, right? Because reciprocal of 1 is 1. So even though they're flipped around, they'll have that same pi over 4 1 point. Right over here, right? And so that means it's going like this. Yeah, it's the reciprocal of the other one. Exactly. Okay? So pretty easy, right? So those are 2 graphs that you're going to need to know. All right? And now I'll talk about the last set, which is these 3. These are kind of weird. Y equals sine inverse. Y equals cosine inverse. And y equals tan inverse. Now here's the thing. On the test, all you'll have to do is show me one of those. And I will let you choose. The easiest one to me is tan inverse. No, it's actually the easiest. Now, what do we remember about inverse functions? This is what we're doing, right? An inverse function here. So we know that sine looks like this, right? Sine goes like this. You agree? Cosine goes like this. I'm just doing the normal ones. And tan look like this. Right? Now, what do we know about inverse functions? What gets reversed? Yes, good. The x and y switch around.
I'm going to hang on x and y on that, but we're going to do
Oh, yeah. The x and y switch around, right? Agreed? So basically, yes?
the opposite again, like
Well, again, depending on how you say opposite, right? So here's the thing. Another way of saying that is that the domain of one is the range of the other, right? If the x values in one are the y values in the other, right? So the domain of one is the range of the other. So in this curve, this is kind of where I'm going to start with the sine inverse. I'll do them in blue. You can see that this goes from 1 to -1, right? Agreed? So that means that's the range of sine, right? So that means the domain of inverse sine is going to go from -1 to 1. The y values here become the x values here. Yeah, and you're kind of thinking, right, what's going to happen with this curve, instead of wrapping around this way, it's going to wrap around like this way, around the y-axis, right? Okay? Yeah, helix, double helix. Now here's the thing. Here's the thing about it, though. It would wrap around, but the problem is a function is not supposed to have this kind of behavior. I'll draw it up here. It will be going something like this, right? But the problem is you can't have a function where the line can go through twice. Remember that from grade 10? Yeah, you would do that vertical line test, and if it goes through the place twice, it's not a function, it's just a relation, right? Right, that's because the guys were cheating on the girls, right? That's what we talked about in our space.
I remember that. Yeah, we didn't do that.
So anyway, the point is that we can't draw the entire graph. We can't draw this whole thing. So what we do is we just draw it from here to here. So it goes like this. It's just this part. Yeah, it does kind of look like a tan. Yeah, if you would think that. But it's got different scales, right? Tan was negative pi over 2. But you're right, it kind of looks like a tan graph. And it's going from pi over 2 in the top to negative pi over 2 in the bottom.
Why is it pi?
Well, because, again, they switched, right? This would have been at pi over 2, right? If this is pi, this would be at half a pi. So that got rotated there. Okay, so that's sine inverse. You can draw these in your notes as you're going along, because that's going to be the question. Cos inverse, same thing happens. And this is why on your calculator, when you press the inverse sign of a ratio, you only get answers between positive 90 degrees and negative 90 degrees. Right, your calculator never gives you an answer of negative 120. It always gives you answers between negative 90 and positive 90 when you do inverse sine. Now, cosine is a little bit different. It's the same idea. You know, cosine goes from negative 1 to positive 1, correct? Right? So that means the domain will be from negative 1 to positive 1. Is that okay? Now here's the thing with cos. If you do the inverse cos of a negative value, someone do it. Inverse cos of negative 0.5.
In this case, the domain is no longer negative. Error 2.
No, negative 0.5 you should.
120. Oh,
120. So, yeah, this is different, right? You get 120 degrees. So cos, the cos thing, we go here from 0 to pi. So that's the section that we take for cos. All right? So it goes like this. And cos goes through the graph like this. Yeah, exactly. That's a harder one to remember, right? Sine kind of makes sense because you can just see that you're...
Then it comes out of the middle.
Yes.
Oh, but you also have to have the scale.
And basically, we're cutting off this part of the graph here and switching it around, right? No. This part of the graph, right here. Switching it around. Anyway, that's one of them that you can draw. Again, they're all from negative 1 to 1, right? So that's a nice thing. This cosine just stays on top, right? Okay, the tan inverse one is this one. And like I said, this is probably the easiest one. Megan, Michelle? This one has asymptotes at x equals pi over 2 and negative pi over 2, right? Those at the x are vertical asymptotes. So what do you think is going to happen to the inverse? If the original has vertical, they're going to be horizontal, exactly. So we're going to draw asymptotes at negative pi over 2 and positive pi over 2. So that makes sense. I like that. It also has the point 0, 0 if you switch around 0, 0. Now here's the thing. The only thing is that the curve is a little bit wonky. The curve has to go this way. Yeah, you flip it and then reverse it. That's another way some people do it. Yeah. It also makes sense because we know if a curve has a curve this way, then its inverse is going to have a curve the opposite convex, right? Yeah, that's the way some people do it. Okay, anyway, so you have to be able to do one of those. Okay? And the last graph we're going to do is one like this. Well, this is so those, again, people, those are 3 sets of graphs, right, that you can do, and you can just memorize how to do them. I'm not going to change them up on you at all. So that's 9 out of 12 there just for memorizing. Well, you have to do both the tan and the cotan, right? And both the secant and the cosecant, because you don't know which one I'm going to give you. But 9 out of 12, and then the last. Here's another one that you can do. There will be some kind of transformation like this. let's say I have this one, y equals the absolute value of 2 sine x plus 1. Okay, yes. So look at this graph. All with these type of transformations, like I've told you before, you may have learned in that one assignment, you just kind of do it in steps, right? This part here in the middle, with math, you always work from the brackets out, right? So the first thing that we're going to do is look at y equals 2 sine x. We're going to graph that first. Okay, well that's not hard. Sine curve goes like this, right? And it's going from 2 to negative 2 now. Good. And my end spot is 2 pi. Well, no, now I'm going to do the absolute value. What does the absolute value do? It makes the points below go above, right? Yeah. And then we're going to shift it up 1, exactly. So instead of starting here, it starts here. It's going to go.
Wait, what?
Well, where will it go to? Yeah, it'll go between 1 and 3, and this will still be 2 pi. This graph brought to you by the Golden Arches. Call it the McHappy graph. Here, no, you got to do it in the right order, Michelle. Once we take the absolute value, that makes the graph now like this. And then we're shifting that up 1. So those type of graphs, you just kind of draw the original, work your way through it. All right. Again,